Hello, so welcome to the revision lesson. It's period one. Period one lesson, you'll be doing some revision, and then period two, you'll have your test. So you can do your own revision. You don't have to follow this revision, and you can skip any topics as well. As that will become more clear what I mean by that when we go forward. You'll see that there's different topics in the topic checklist, and you can skip those until you reach the topic checklist, which is appropriate for you. So please write the date. Sorry, the date will have changed by now, but please do write the date that it is today, and then revision. And then your first 10 minutes you can spend using these pages, BBC Bite Size 1 to 4, and I've put it in the link below as well, in the Firefly page below there, so you can access it via that, or you can type it in, which might be a bit tedious. Please do use these pages to read, and then there's a test as well at the end there. This shouldn't take any more than 10 minutes, and the test is literally a minute test. So even if you don't want to read the pages, you can just go straight on to the test, and vice versa. Okay, so this is a topic checklist. This is in your experiment book on page 27. And please do pause this and just read through each of these topics and see if you've got it. You can screenshot it, then put it in your OneNote under a page called revision, and yeah, then just tick whether you need help, or if you're okay, or if you're prepared for it, and read through each of these points. This is everything that you should know for your test, and in this video we're going to just break down each of these topics, so you can skip forward to any topics which you feel like you would prefer to focus on. So the next topic is looking at how the atmosphere has changed in terms of three different gases: water, oxygen, and carbon dioxide. I just want you to pause this video. Perhaps you can copy out this table and think about some of the reasons why there was a change of this gas in the atmosphere, or you can maybe write down the reason. We'll go over the answers in a moment. Please do pause. Okay, so water, as you can probably remember, that the Earth at the start was at the very beginning was very hot. As it cooled down over time, the water vapor in the air condensed to form oceans and seas. Your oxygen, however, that increased, and that was because of photosynthesis. So as time passed, there was more bacteria, algae, and plants, and they photosynthesized to get their food. So as their population increased, photosynthesis also increased. So this so the oxygen levels increased. This also means that the carbon dioxide levels therefore decreased, and that carbon dioxide became kind of stored in plants. So the plants would use the carbon dioxide to make food, and therefore the carbon is then stored in this food here, and would use this food to kind of build cells. So your carbon dioxide is actually being stored in plants or in trees or in bacteria or algae. And when we burn trees and plants and stuff, we can release that carbon dioxide back out into the atmosphere. But trees essentially are a carbon store, and we're carbon-based life forms. So when we die, we actually plants and animals become fossil fuels and sedimentary rocks in certain conditions. So sedimentary rocks and fossil fuels are also considered a store of carbon or carbon dioxide. Oceans as well, carbon dioxide can dissolve in oceans. So carbon dioxide is a soluble gas. It can dissolve in water. When it does, its state changes. It becomes aqueous. It's the same thing that's in fizzy pop is carbonated water, which is carbon dioxide dissolved in the water. And as you may already know, it becomes slightly acidic. So you should already know that you may already know that fizzy drink is slightly acidic, and that's why it's bad for your teeth. Okay, so the next topic here is to know the approximate percentages by volume of the four most abundant gases. And here we are, this table here. You should know these values. Next one is describe how the air is separated into its constituent gases. So I'm just going to go back onto dry air actually. It is dry because there's no water in it. Now, we haven't included water here, but just because the percentage abundance of water can change. It could be anything between almost 1% to really almost like 4%. So it can change depending on humidity. So it can be quite confusing. So we normally look at dry air when we're talking about the percentage abundance of these things. So we're now looking at how we can separate these gases in dry air, and we can use fractional distillation here. So first what we do is we get dry air, or actually we just get normal air, to be fair. We just get normal air and we just liquefy the air. So it's liquefied air, and we cool it down, we cool and compress it, we cool it all the way down to minus 200 degrees Celsius. And at that temperature, but when we start cooling it down, your water will then liquefy. We can remove it by absorbent filters. So we start off quite high. We start off at like a kind of a temperature around here, around like room temperature, and then as we cool down, we can remove the water already, and then at minus 79 degrees, your carbon dioxide freezes. So we can remove that. As we keep going down, we would then, your oxygen, argon and nitrogen, and they will all liquefy. So we'll have a liquefied mixture of these three gases. And those three gases we can actually put through what we call a fractionating column here. A fractionating column. I'll just write it at the top there. It is, and with this fractionating column, put bad man right here. Fractionating column. Now, these are the steps to what happens. So air is gradually cooled to minus 200 degrees Celsius. Water and carbon dioxide are removed first, as they have the highest boiling points, so turn into liquids and solids first, and they can be easily removed or separated from the gases. Liquefied nitrogen and oxygen is gradually warmed from minus 200 until they separate. So if we look at the gases in here now going through, we've got oxygen, argon and nitrogen. We're going to ignore argon because there's such a low percentage of it, and that's removed at a different stage, which you don't need to know, so don't worry about argon. We're just going to be looking at your oxygen and your nitrogen. So let's say your oxygen and your nitrogen come through here, and then your liquefied nitrogen, oxygen, is gradually warmed from minus 200 until they separate. So you can see here that your nitrogen is going to go from liquid to gas. So as we go up here, we're going to go from liquid to gas as we reach their boiling point. So we reach nitrogen's boiling point, so it turns to a gas. So your nitrogen kind of goes up, it's less dense, so it rises, and it can be taken out via the pipes at the top. So nitrogen boils first, and then liquid, and then your liquid oxygen. So we stay at this temperature here to prevent the oxygen from boiling, and the oxygen can just be removed from the bottom. Okay, so there's three experiments that you need to know about how we can calculate the volume of oxygen in air. And that can be calculated by these three experiments, with phosphorus reacting with the oxygen in the air, copper reacting with the oxygen in the air, or iron reacting with the oxygen in the air. So in all three of these experiments, you have oxygen reacting with a substance, and then because the substance only reacts with the oxygen in the air, we can calculate how much oxygen was actually in the air if we calculate the volume of gas before, then the volume of gas afterwards. So all of these three experiments work on the same principle, and indeed any other experiment you'll see related to calculating the percentage of oxygen will work in a similar way as well. So one common question they may ask is, what is an error in these experiments? And in pretty much all of them, it's ensuring that you have enough of the substance of phosphorus, copper or iron in excess, so all the oxygen reacts. So you want to make sure that all the oxygen in the system has gone, so you get a good calculation. If it's not all gone, then you'll get a lower reading for oxygen. You won't get the full percentage. Okay, so all of the oxygen reacts. There's two things. You need to ensure that there's enough of the substance, or it's in excess, and you need to also ensure that you leave the reaction going for long enough so that as much of it reacts as possible. So phosphorus this reaction here will stop on its own accord. With copper, you have to keep putting the syringe in and out and drawing the oxygen over the copper to ensure that all of the oxygen reacts. When the copper stops reacting or changing color or whatever, you can stop the experiment. And with this experiment in particular, you want to ensure that you're waiting for long enough. So this is about a week or so, and nothing under a week, because it takes a long time for rusting to happen. Okay, so if you don't do those things, then the percentage of oxygen calculated would be lower. This is the calculation that you can use. Total volume of oxygen over the volume of oxygen divided by the total volume of gas in the system. So in the first one, if you had 100 centimeters cubed of air in here, then at the end of the reaction, you had 80 centimeters cubed of oxygen. You can do 100, which is the total volume of gas in the system, divided by, you have to do 100 minus 80. So 100 minus 80, which is equal to 20. And so 20 over 100, so 100 minus 80, 20 over 100, then times that by 100 to make it a percentage, and you'll get around 20%. Okay, so there's 20% of oxygen in here. Your next one, we've got some results here. Initial volume of the system, this is easy as well. So we've got, we're going to do 100. We're going to find out how much oxygen is in the system, how much oxygen was removed, and it's 100 minus 79, and that equals 21. And if we do 21 divided by the total volume of air in the system, that's 100, times it by 100, and that equals, as you could probably already have guessed, it's 21%. So here now, this one's slightly different because you need to take the total volume of air in, you need to do the total volume of gas in the whole system. So that's here in the conical flask, in the delivery tube, and in the syringe as well. So let's see some results here. So we've got total volume of air in the conical flask is 130. Let's calculate the amount of the volume of oxygen first. So you've got initial reading on gas syringe is 92 minus 43, because that's the reading afterwards, and that equals 49. Now we can do 49 divided by the total volume of air in the system. That is 130 plus 12 plus 92. That was the total volume at the start, times by 100. Now you should get around 20.9%. Okay, 20.9%. Now here's an example question which you can try yourself here for those questions. I'm just going to pause it, and please do answer these questions in your OneNote or on a sheet of paper, then upload it to your OneNote revision page. Okay, so we're just going to go through the answers now. So calculate the percentage oxygen in the air using this data. So we've got 95 centimeters cubed at the start, and we're going to minus 80 from it. So this is how much oxygen has reacted. So that's going to be 15 centimeters cubed of oxygen. Now, to work out the percentage of oxygen in the air, we need to take 15 divided by the total volume of air at the start, which was 95. And then times that by 100, very easy. And that's going to equal 15.8. And that sounds quite low to me. It's meant to be, you should know that, as you know, it's meant to be around 20-21%. You can see here that it's because I've left it for 2 days, so they can just leave the reaction for longer. So leave the reaction for longer, perhaps around a week. Okay, that would achieve better results because perhaps not all the oxygen's reacted, and therefore you should be getting a higher result, maybe closer to 20. Okay. Okay, so your next topic checklist is writing word equations for all the oxidation reactions that you've come across. So they're all pretty much the same. They follow the same pattern. You just need to know that you just need to be careful with the ending. So it does change to oxide and not phosphorus oxygen or copper oxide or copper oxygen. You have to change the ending to "-ide" or you won't get the mark. Oxidation reactions. These are all oxidation reactions as oxygen's been gained. But the phosphorus one, this is also combustion because, as you can remember, light and heat energy is given out. So you can test whether these products, so whether the products here, so these are all the products because they're produced in the reaction. On the other side of the equation is the reactant. So the reactants react together to form the products, as you already know. To test whether the product is acid, well, whether these products are acid or alkali, there's a two-step procedure here. You can add water, and you'll get 1 mark for that in the exam by saying add water, and then add universal indicator solution. You'll get another mark for saying that if they say what is the procedure to test whether products are acid or alkali, and you can say that. Now, all of your metal oxides are bases. So metal oxides are bases, and non-metal oxides are acidic normally. So phosphorus oxide, if you dissolve it in water, it's acidic. Carbon dioxide, if you dissolve it in water, it becomes carbonic acid and becomes acidic. Or sulfur, sulfur oxide or sulfur dioxide, dissolve it in water, become sulfurous acid. So. Okay, your next one is some examples of exothermic reactions. An exothermic reaction is just release heat energy to the surroundings, and these are some examples here. And then your last part in your last topic is describing the method used to investigate flame colors, and this is your flame test procedure. Platinum or nichrome wire, and it has to be platinum or nichrome. That's just because these don't color the flame, so they don't color the flame, and they have a high melting point. So there's two reasons why they don't color the flame, and they have a high melting point, so they won't melt when you do it. So there's two reasons why we use platinum or nichrome wire. Then you place the sample in a blue or roaring flame. It has to be blue or roaring, and that's just so the color isn't affected. So with these tests, it's all about the color, so the color isn't affected. Okay, also you can see it clearly, so color isn't affected, or sorry, masked, isn't masked. Okay, so those are important. Now, it says here, know the flame colors. Now, these are all the flame colors. Note, you would know that lithium and strontium, they're both red, but don't worry about that at this stage. They're both red. In an exam, if something comes up red, just go for the lithium.